Did you all have fun on problem set 2? Yeah, it's exciting. Did anyone have fun? 1? Only 1? 2, 3? Oh, good. Anyone find it overly painful? Couple? Okay, so we're somewhere in the middle. Good. Problem set 3 is out now. You can find it on the web page. And any questions before we get started? Good. So today we're going to talk more about sorting. And we're going to ask sort of the question that should have been bugging you, which is how fast can we sort? So what that means is if I give you n numbers, how long does it take to sort them? What's the answer? N log n. Right. So we've seen a bunch of algorithms, and the best one that we had was n log n. So the good, n log n. The kinds of algorithms we've been looking at are called comparison sorting algorithms. So comparison sort is one where you only use comparisons to learn information about the input. So you're given some set of elements, of numbers, and they're in some order initially, and you want to find their sorted order. That's the sorting problem. One way to learn things about their order is by comparisons. And all the sorting algorithms we've seen, so we've seen insertion sort, we've seen, what else have we seen? Merge sort, quick sort, and heap sort. All of these algorithms are comparison sorts. All they do are compare the elements. They also swap the elements, but swapping the elements is just for moving them around. It doesn't tell you any information about their initial order. Okay, so the way that we learn information, and information will come up later in the lecture, is by comparisons. And you should start thinking now, and later on I'll ask, what other things could you do to learn information about the order of the inputs? Okay, so for now, let's just think about comparisons, but we're going to talk about other sorts of algorithms later on. Okay, let's maybe do a bit of review. How fast is insertion sort in the worst case? N squared, good. Merge sort, n log n. Quick sort, n squared, good. In the worst case, but if you use the randomized version, then you get n log n expected. And heap sort is n log n. That was a little quieter because that's more recent. There's less time to set it in. So the best comparison sort we've seen runs in n log n time in the worst case. And what we'll prove today is that that's optimal. You can't do better than n log n. So this is called a lower bound, saying, well, that's the best you could hope to do. And so these merge sort and heap sort are really good algorithms in that sense, that other than this constant hidden in the theta, they're doing the best you can do. So that's cool. Now, to prove that, we're going to use something called decision trees. So the easiest way to describe a decision tree is to do an example. So in general, suppose that you want to sort n numbers and call them A1 up to AN. And let's look at the example where n equals 3. Okay, the idea with decision trees is, well, all you can do is compare the numbers. So for example, we could compare 1 versus 2. Okay? And I'll be assuming for now that all of these AIs are distinct. So none of them are equal. So the answer to this question, how does 1 compare to 2? How does A1 compare to A2? Is either A1 is less or A2 is less. Okay, so that's like branching in a tree. So this branch is representing that A1 is less than or equal to A2. And this branch is representing that A2 is greater than or equal to, A1 is greater than or equal to A2. Two wrongs make a right, so good. So let me just draw a sample decision tree. Okay, so this is a decision tree. And what the leaves mean, I'll also write down the general form here. The leaves are telling you what the final order is. So 1, 2, 3 means that the numbers were in sorted order. Okay, so why is that the case? So following along, this branch means that A1 is less than or equal to A2. This branch means that A2 is less than or equal to A3. So why do we know it's in sorted order? Maybe, sorry? Transitivity, good. When you know, we have this sort of picture, right? We've made this comparison, we've made this comparison, and so that has to be the way they're laid out. Good. So the general form of a decision tree is each internal node here is labeled I:'j, which means compare AI with AJ. And good. So the left subtree of one of these comparison nodes tells you what to do, so which comparisons to make if AI is less than or equal to AJ. And the right subtree is the other way around, if AI is greater than or equal to AJ. Okay, so that's just a general picture of what's going on here. Okay, this is somehow describing an algorithm. Right, you could implement this. You could say if A1 is less than or equal to A2, then do this stuff recursively, and otherwise do this stuff. All right. Doesn't seem so profound, but this will be a very useful tool for proving lower bounds. Okay, let me say what the leaves do. So the leaves give us a permutation of the AIs. And that permutation specifies that we now know the sorted order of the AIs, of all of them. And the sorted order is given by this permutation pi. Now, having done problem set 2, you all are happy with permutations as functions, right? So this just means where does 1 go, where does 2 go, where does n go? And that's what these pictures are saying. Here it's saying the sorted order is you take A2, then A1, then A3. Okay, let's do an example so that to make this more concrete. Let's suppose that our numbers are, maybe I'll use another color. I thought I'd upgrade and use colored chalk just for added content. So let's suppose that our numbers are 9, 4, and 6. Okay. So which way do we go here? To the left? To the right. Good. I mean, 9, A1 is bigger than A2. Okay, so we go this way. Which way do we go here? Right. Good. Because A1 is 9. That's bigger than A3, which is 6. Which way do we go here? You're getting bored. Left, right. A2 is 4. That's smaller than A3. And so the claim is that the sorted order is 2, 3, 1. Is that right? Well, A2 is the value 4. A3 is the value 6. A1 is the value 9. Cool. Sorted. And you can check all the possible outcomes here. It's right. Okay, and you can go through a formal proof of that by saying, well, A1 is larger than A2 and larger than A3, and A2 is larger than A3. Then you know the sorted order has to be this permutation. Okay, so that's the idea with decision trees. Now, how do we use decision trees? I said a decision tree is like an algorithm. And in fact, the converse holds. An algorithm is like a decision tree. Okay, if you think for a moment. So we can use decision trees. Oh, more color. Not very thick chalk. Okay. So if I give you any comparison algorithm, I claim you can represent it by a decision tree. Well, actually, not just one decision tree, but you need one tree for every n. Okay. So how do you do it? How do you find the decision tree that corresponds to an algorithm? A comparison algorithm. Any ideas? Yeah? Right. Right, so you start, the initialization is just the root. And what's the content of the root? You recursively split. Yeah. And every time you go through a loop. Any other ideas? Close. When does this tree split? Sorry? Every time you use an if-else statement. Yeah, so every time you branch. But more importantly, every time you compare. Right? But that's sort of the same thing. And comparison sorts, well, okay, there are two ways you could branch. One is because you're comparing elements, and the other is that you're just comparing indices. Right? So it's not every time you branch, but it's actually every time you compare. So we'll view the algorithm as splitting the tree for each comparison you make. Okay, so when this algorithm, the first thing it does is compare 1 and 2. And then which way it goes depends on which comparison it makes next might depend on whether A1 is less than or equal to A2. It might depend on what the answer to that comparison was. So we should split. And this is one case of the algorithm. This is the other case. I mean, this is going to branch a lot. You're going to get some exponential size tree, but it's OK. So what does this tree represent? Thinking back to problem set 2 so long ago, I mean, what is this tree giving you? Yeah?
The trace of the execution.
The trace of the execution, right. This is all the traces, in fact. So this is, the tree represents all possible execution traces. Exactly. OK, so this is an idea that you know and love by now. I mean, we're just seeing what all the possible things the algorithm could do. That is the decision tree corresponding to a given comparison sort for a given n. Okay, and you can do this for every n. You get this family of trees. Now, what can we do with this tree? I claim one thing that we can learn from the tree is what is the running time. So the running time of an algorithm, I mean, this is not one number. Running time depends on what the input is. So if I give you an input, how would you measure the running time of this decision tree in terms of the number of comparisons? Yeah? The height. Yeah, so let's say the length of a path from the root to the leaf. Good. So in this example, I made 3 comparisons before I got to the leaf. Once I got to the leaf, I knew the answer. So the running time there was 3 comparisons. What is the worst case running time? So if I consider all the possible inputs, the longest path. Yeah, that's called the height of the tree, right? So now you start to see why these things might be useful. Right? Not only is the decision tree modeling the algorithm, you can very quickly see how long the algorithm is taking in the worst case. You just measure the height. Okay? This all seems simple, but now you might say, well, gee, I don't know how to prove that sorting takes n log n time. But in fact, now that we have this set up, it's totally easy. So why don't you think about how we should prove this while I erase the board and write the theorem. So we want to prove that any comparison sort takes n log n time. So one way to say that is if we have any decision tree, that's correct. So it sorts n numbers. Boy. Then that decision tree has height. Oh, this is much better chalk. At least n log n. So that's the claim. Let's see, are there any ideas on how to prove this? Looking at a decision tree, what could we count? What do we know about these decision trees? We want to know its height, but we don't know its height at this point. Do you have an idea?
They must give a total ordering on, say, the permutation from 1 to n max with n part and then the log n calculation values comparisons, and then sometimes they'll give a complete total ordering.
So your idea is, well, we need n comparisons just to be sure that we have them in the right order. But then we have to find that order in the first place, and so there's this log n for figuring it out. So yeah, that's roughly what's going on, but it's not a proof. You have an idea?
Well, what we can say is that we know how many leaves have to be at the bottom.
Right. You know the number of leaves. How many leaves there have to be? The number of permutations of n. Right.
And then we can just...
Okay, well, that's good for now. We'll come back. So exactly. We know that the number of leaves in the tree has to be at least the number of permutations on n numbers. Why? Someone other than you. Why is that the case? Yeah. You have to have every permutation as a leaf, right? Okay, that's sort of the same thing. But, I mean, what property of the tree is telling us that? Yeah?
It's correct that it always
Correct.
says
Right. So this is just from correctness. Just sneak this in here. Okay. Why is this greater than or equal to and not equal? This is something I was thinking about last night. Gee, it has to be equal, right? How could it possibly be greater? Yeah? There could be multiple paths to the same answer. Yeah? Why? Yeah?
Because you might have equal elements that compare equal.
Elements that compare equal. So actually, I'm assuming here that all the elements are distinct. So that, I mean, you're right, that there can be multiple paths to the same answer, but it's not intuitive why. Because at the top node, right, it says, is 1 less than 2 or is 1 bigger than 2? A1 and A2. If you go left, that's a completely different set of permutations if you go right. There's no way, if I go left, I could get the same place as one of these as one of these. Yeah?
Well, but the way you drew your graph, you could have flipped the two branches on either side. So if like 1 and 2
Right.
are equal to each other, they're sort of, it would be the same if you were down the left side or the right side.
I mean, yeah, these pictures are symmetric, but so I've defined, wherever I define decision tree up here, the left is always when AI is less than or equal to AJ. So in all of these leaves, 1 comes before 2. And in all of these leaves, 1 comes after 2. Yeah?
Well, for insertion sort, I don't think that you can necessarily get two things that are the same path. If you take something like quicksort, obviously depending on what you choose is X, each time you're going to have a different permutation that gets to an ordering.
Right. So quicksort, there are different pivots you could choose, and you might get to the same. You should get to the same permutation no matter which pivot you choose. But that's sort of changing the algorithm. So I think this is a tricky notion why this can be greater. And the problem is here, it's not at all intuitive what's going on with the decision tree. Because this is not pseudocode, right? You can implement this sort of thing, but for general n, writing down the program, it's not so easy just to go and implement a decision tree for general n. So the difficulty here is that the algorithm can do stupid things. It can compare the two elements twice. It can compare AI and AJ early on in the tree and then compare them again. Not very exciting, but you can actually get more leaves in this way. So I won't say any more about that because it's not so exciting, but this can be greater. It's also transitivity. Right? You compare AI and AJ and AK. You could later compare AI and AK, and the answer is forced. OK, possibly. Good. Now, we want to talk about the height of the tree. Right, so how can we connect the number of leaves and the height of the tree, h? Yeah?
It's 2 to the h. The number of leaves are going to be less than or equal to 2.
Right, number of leaves is less than or equal to 2 to the h. Good. So that's our connection. These two things are the same. So if you look at it, with your head on backwards, then 2 to the h is greater than or equal to the number of permutations on n numbers. What's the number of permutations on n numbers? N factorial. So that means that 2 to the h is greater than or equal to n factorial. So now we want to solve for h. What should we do? Take log base 2, yeah, of both sides, right. Let's see. Maybe I'll use this board if you don't mind. Seems I've etched into this board, so it's not coming out. Good. So we take log of both sides, and we get that h is greater than or equal to log of n factorial. What property are we using in this step? Why can we get this implication? Yeah? Log is always increasing, right? Remember, you have to be careful with inequalities. So you need to justify these sorts of steps. Let's see. Now we need to know what log of n factorial is. Does anyone remember Stirling's formula for n factorial? 1. Sorry? It's roughly n to the n. It's not actually order n to the n, but it's at least n over e to the n. Put in some parentheses to be clear. So yeah, you can think of it as roughly n to the n. The e to the n is certainly smaller, but it's not a constant. E to the n is not constant. So this is Stirling's formula. And so you get a lower bound there. And now we can take logs. So what is the log of this? Practice your log formulas. Yeah?
N log n minus n log e.
N log n minus n log e, right. Cool. So this is order n, right? This is a constant, log e. This is n log n. So this is at least to a constant n log n. So we proved that the height of the tree, the decision tree, is at least order n log n. We're done. Wow. That's it. That's all you have to do to prove that the worst case running time of a comparison sort is order n log n. So aren't decision trees cool? I mean, it doesn't get much easier than that. All right. This theorem also tells us something, and I'm curious. So I was talking to a TA, and I called this a corollary. And she had no idea what I was talking about until I wrote it down. How many people say corollary? No one. One person. How many people say corollary? Everyone. Wow. Are you Canadian by any chance?
Yes.
Oh, God. It's a Canadian thing. All right. That explains it. Good. So this is a corollary. Well, we have two algorithms that we've seen, heap sort and merge sort, that run an n log n time. And so the corollary, easy corollary, is that these are optimal. They're optimal comparison sorts. And so sorting takes n log n. That was the original answer to the question I asked in the beginning of lecture. And now we're going to prove that that's wrong, just because we like to make trouble. So has anyone had an idea of what things could you do to sort other than compare the elements? This is not a well-formed question, but I thought I would ask it just to see if you had any good ideas. No ideas? Drop them into buckets. Cool. Somebody has been using punch cards. Right, that's what people used to do. I'll talk about that a little later. Take a bunch of cards, you sort them into buckets, and you do. Now, sorting into buckets is not exactly comparison, right? So if I want to, so suppose I have some. Okay, I'm getting ahead of myself. But suppose you have a 5-digit number. Okay, I look at the first digit. It's between 0 and 9. I have 10 buckets, and I put it in the right bucket. I'm not comparing cards. I'm not looking at 2 cards and saying, is this 5 bigger than this 6? I just say, well, this is card number 5. I put it in the 5 slot. It's not a comparison. Right, so that's something else we could do. And the first way, so we're going to use that idea in two ways. The first algorithm is called counting sort, and the second algorithm is called, boy, I've forgotten, radix sort. There's also a bucket sort, but we won't talk about that in lecture. Good. So what does counting sort do? It's not going to make any comparisons. And it's going to use this idea of buckets. And so the input, we have some array, A1 up to AN, with a property. So this is going to assume something about each AI, that it's at most, let's say that it's an integer in the range from 1 to k. And the output will be the sorted version of that array. So we're sorting numbers, but we have some bound. We know how big the numbers can get. They can get at most k large. We'll also use some auxiliary space. So this is just declaring my variables. C from 1 up to n. And so we'll just have n numbers floating around. Sorry, actually not 1 up to n. It will only be 1 up to k. So this is sort of depending on some property of the input that's not just the input size. It's sort of the size of the numbers that you're dealing with. OK, now let's write the algorithm. Maybe I'll use 2 boards vertically aligned. That would be clever. So the algorithm is, first thing I do is not very exciting. I'm just going to initialize C. I want to get all the labels right here, so. that clear? Okay, this is maybe one of the most complicated algorithms written in pseudocode we've seen so far. Now you really see why you need either an English description of what's going on here, or a picture, or an example, or something, which is what you're supposed to do in your problem sets. So let's do an example. Good. So let's suppose that our array A is 4, 1, 3, 4, 3. So I'm now allowing repeats. Okay, I can have duplicate elements. B will be our sorted list. I want to annotate this a little with the indices. This is A1, A2. And we'll compute something called C, which, well, all these numbers are between 1 and 4. So C will have 4 entries. Initially, they're all 0. Okay, so the first thing is just setting all of C to 0. The second step, I claim, is just counting how many keys are there equal to a particular value I. So there's one spot in C for each potential value. Right? 1, 2, 3, or 4. If I look in the array A, well, there's 1, 1. So I claim that C will set C1 to be 1. There are 2 3s. So I claim that we'll set this one to 2. There are 2 4s. And there's no 2s. So I claim that after this after the second loop, that's what C will look like. Okay, so that should be fairly clear. The key here is that we're indexing C by a value, not by one of these indices that we're looping over. Okay, I'm looking in the array A. So in the beginning of the loop, I look at the first element of A. I say, well, that's the number 4. I will go to the 4th position in C and increment that number from 0 to 1. The next time I see 4, I'll increment that number again. So this is where we're learning something about the input, about its order, and yet we're not doing comparisons. We're doing this indexing operator. So that's what's cool about counting sort. This is really, right here is the heart of counting sort, and the rest is cleaning up and getting things in the right order. Okay, this is clever, but this is really what's essential in counting sort. All right, so let's go on. Let's look at the next loop. So this next loop is saying, this next loop is incorrect. Thank you. It says take what I used to have in C and what's in the previous position in C, add them up and set that to Ci. So it's not going to change the first entry of C because I starts at 2. Okay, but then the second entry, it says, well, I'll take this number and I'll take this number and add them together. And then I'll take that number that I just computed and this number 2, add them together, I get 3. And add these together, I get 5. Okay, so this comment is saying, well, what that's doing is just keeping running totals, right? So 3 is the sum of everything left of here. 5 is the sum of everything left of here. Okay, so this is the number of values in here that are less than or equal to 3. Good. Now the last loop is where all the fun goes on. This is where we actually do swapping, more or less. OK, so J starts at n, and it goes down to 1. So the first time J is here. And we say there's this triple bracket, which makes a lot of fun. So AJ is 3. CAJ, we look in C at value 3, that's 3. B of 3 is what we're going to set. OK, so just keep track of here. This is B of C of J. for this step. And we set that to A, sorry, wrong, A of j. Thank you. It's messier, it's less messy than it looks. And we set that to aj, j, so we set that to 3. So we're putting 3 there. You got a question? No? OK. So we actually move this 3 over here. You can think of it that way. Notice we were using 2 different arrays. So I'm not going to overwrite the a's. That's good, because otherwise I might have just clobbered a value there, using a different array b. Now we decrement the counter that we just used. So we use this number 3, cross it out, and write 2 instead. And if you think for a moment, what that means is the next time I see a 3, I'm going to put it in position 2. The 3 from A went into B, not from C. Because we're setting this B thing, B bracket whatever, to be A bracket A bracket J. Right. So this last loop is hard to wrap your head around, but let's do a few more steps and it should become clearer. So the next step, J is 4. So we look at the number 4. We look at C sub 4. That gives us the value 5. So it says 4 should go to position 5. That wasn't so bad. And we decrement that counter, which means the next time we see a 4, we'll put it here. Now we look at the value 3. So J has moved over here. 3, we look at C sub 3. That gives us now the value 2. So we put the 3 in position 2 of B. And we decrement that counter. And then we go back. J is 2. We look at the A sub 2. That gives us 1. We look at C sub 1. That gives us 1. So 1 goes in the first position. And finally, we go here. And it better be that 4 goes into the empty spot. But let's check. We look at A sub j. That gives us 4. We look at C sub 4. That gives us 4. And so the 4 goes in position 4. Pretty neat. I mean, that should the 5. Yes, thank you. Sorry. This is position 5, but value 4 is copying that one. But otherwise, we're doing good, right? This is the sorted order of that. Perfect. It's maybe a little mysterious that this works until you prove to yourself that it's correct. So is there some kind of loop invariant that we can give here to prove that this is correct? I haven't actually thought about this, so this is just on the spur of the moment. Is there a good loop invariant that will show what's going on here? Probably not. Sorry. I mean, there may be, but I can't. Oh, you have one? In the second line. Here. Well, OK. Yeah, so this is a good invariant. So we believe that. But in this loop, I don't know if there's a good invariant. I think it's just the property that we're counting how many 1s there are. And there's 1, 1. So we reserve space in the beginning of the array of size 1. And that's where all the 1s will go. Then the next value is 3. And there are 2 3s, so we'll reserve the next 2 positions for 3s. And then we'll reserve the next 2 positions for 4s. And these running totals are telling you where the last guy is. So this, if you look at the initial value of C, it says the last 1 is in position 1. The last 2 is nowhere, is not here. The last 3 is in position 3. And the last 4 is in position 5. Okay, and then we're just putting the 4s in reverse order, and then putting the 3s in reverse order, and the 1, and so on. And that's why you're getting this decrement. Yeah?
The things that AI could do aren't necessarily numbers, but I don't see why you just don't say, okay, the first element of B is 1, then there are no 2's, and then there's 2 3's, and then there's 2 4's. So it's just
Sorry? Okay, there's two things going on here. So let me repeat the question first, if I remember all of it. So the first thing was, we're assuming that the elements we're dealing with are numbers. So that's right. And then you were saying, well, why do we have to go through all this counting sort stuff? Why can't we just count the numbers and then say, okay, look at the ones. There's 1 1, so I'll put it here, and then increment j, and then there are 2 3's, and so I'll put them here. So I challenge you to write down that algorithm. The trouble is it's hard to get that to run as quickly as counting sort does. Because how do you find the 1's? How do you find the 3's? Well, that means you need to know them in sorted order already. Right? If I want to say, okay, I know I should write a 1 first, and then I should write however many 3's. So I'll count the 3's and say there are 2 of them, put them there. That's hard because you have to know that 3 is the next number after 1. Yeah.
I think the question is, once you've gotten C in the
Yes.
second loop there, why don't you just run through C?
Okay. So run down C and say, good. Right, there's a 1. Okay, now I understand your point and your question. Good. So you're right. You actually have the sorted order here. You say, well, there's 1 1, so I'll write it. There's no 2's, so I'll stay there. There's 2 3's, I'll write those. And then there's 2 4's, and I'll write those. And then the issue comes up of satellite data. So it may not be that we're just dealing with the numbers here and shuffling the numbers around, but we care about, to each number is attached some other piece of data. Okay, so actually these 3's are a little bit different. They might have different data associated with them. And now it gets tricky because that satellite data has to be put in C as well for the algorithm you said to work. So what you said will work if you're just dealing with numbers, but the satellite data will kill you. And we'll need that later on in the lecture for radix sort. So what's the running time of this algorithm? Order n? This is certainly order n. This is order n. This is order n. So it's order n? Yeah?
For the third for loop, should it be from I to k?
Ah, thank you. Yes. This was n. It should be k. Thank you. I think, yeah, so it actually alternates between k and n. So this does not take order n time. It takes order k time. And so does this loop. So what's the total running time? So we don't really know much about k. So the sum of all these is
Max of n k.
max of n and k. Oh, you've been doing your exercises in problem set 1. Good. It's simpler than that, right? We can just say it's n plus k. But it's also order n max of n and k. So time for counting sort. Well, there's 2 n's and there's 2 k's, so it's order n plus k, which is order max of n and k. So now we get to use our 2-variable multivariate big O notation. Cool. Okay. So it depends on k. It depends on what the input looks like. Right? Not only does it depend on the size of the input, it depends on how big the numbers get. So let's try some examples. Right? What if I had a nice, good 32-bit machine? So all the numbers I'm dealing with fit in a word of 32 bits long. So that means k is 2 to the 32. Anyone have that memorized? 4 million. 4 billion. Yeah, it's about 4 billion. Good. You don't even have to memorize anything for that, right? Because 2 to the 30 is a billion. So that's pretty big, but it's manageable. And so what does this mean? Well, the space that I'm going to use, so the auxiliary storage, which is C, how much is that going to cost me?
More memory than you can address.
More memory than you can address. Good point. Yeah. So it's 4 billion values, and the C's are also integers, which are, say, 32-bit. So that's 4 billion words, which is 16 gigabytes, I guess. Which is a lot. And you're right, on a 32-bit machine, you can't address that much space, which is, assuming you can address each byte individually. If you only have to address words, it might work at the bus level. But so that's not the point. It's a lot of space. It's reasonable if all you're doing is counting sort. You have to sort these numbers really fast, and you've got a lot of numbers to sort, then this is a good thing. But what if I'm sorting 1 million numbers? Then how long does this algorithm take? Order K, yeah, a lot. It takes 16 billion, a lot longer. So if I have 4 billion numbers that I have to sort, then this is doing good. It's actually a linear time sorting algorithm. So I forgot to prefix this whole thing with linear time sorting. That's what we're doing here. So if n and k are around the same, this algorithm is running in linear time and linear space, which is cool. But there's some cases when it's not what you want to do. It depends on the relationship between n and k. So if n is order k, or maybe I should say k is order n, then the running time for counting sort is order n, which is cool. Actually, seems rather contradictory, right? We proved an n log n lower bound. So how could we possibly sort it in linear time if we know that every sorting algorithm has to take n log n comparisons? Because it's not a comparison. OK, I sort of gave this away already. So this is OK because counting sort is not a comparison sort. The lower bound only holds for comparison sort. Sorry, counting sort is not a comparison sort. So we're happy. This is pretty neat. This is first illustration where it really depends on the model of your computation, what you're allowed to do with the inputs. Yeah?
Just a question. It seems to me, though, that the important fact is not that it's... it seems to me you're still doing comparisons, like you're comparing indices, for example, but you have more information with the counting sort than you do with a comparison sort. Like here, you know the bounds on what your input is, and comparison sort that we talked about earlier, you didn't. That seems to me to be the important part, not the fact that it's...
You're right that there are two things going on here. We know more information. We know a property of the input. But even if you know, I should get this right. So even if you know that all your numbers are between 1 and n, comparison sort cannot do any faster than n log n. So you can check the lower bound. So you're right, we're assuming that all our numbers are between 1 and k, but in fact that doesn't help you with comparison sort, and you can prove that. So, I mean, you're right, we have to assume that, and that's key for counting sort. But it's not the whole story. The other thing is that we're allowed to index an array by a value. With comparisons, you can't do that. If you were given, well, OK. This is using more about the value than just comparing two elements at once. This is allowing you to group them into buckets. And that's what I would say is essential to counting sort. Other questions? Good. So counting sort is good some of the time, but not all of the time. And we like to go fast. So let's come up with a better algorithm. Charles, could you get the cards ready? If you have them? Stability. Oh, thank you. Good. So before we go on to the next algorithm, we'll use this algorithm. And there's a property of this algorithm that we'll need, which I can write here. So there's an important property of counting sort. Which is in some sense why we went through all this trouble to go backwards from n. And it's called stability. So stability means that in our input, I've erased the example, unfortunately. In our input, we had equal numbers, like we had 2 3s. And those 3s could have had satellite data attached to them. Initially, this 3 was before this 3. Stability says that once you've sorted them, they're in the same order. Okay, so you preserve the order of equal elements. In the sense that if I put little tags so I could distinguish the different 3s, then I'm actually, if you follow through this algorithm, you'll see that you're always preserving the order. You're never switching them around. Okay, so this is important. You can think about what other algorithms have we seen. We've seen 4 sorting algorithms other than counting sort. Which of those are stable? Okay, some of them are and some of them aren't. So I encourage you to think about which are which. OK. Now we'll go into radix sort. So we're going to use this in our next algorithm. So the idea with radix sort is what I was talking about earlier. Suppose you have a number with several digits. You could imagine sorting those digits one at a time. Okay, so radix sort is a digit by digit sort. And radix sort is the oldest sorting algorithm, I think. Certainly the oldest that was implemented. And it was implemented, let me get the name of the guy who did it. Has anyone heard of Hollerith? No one? Boy. So the origin is the original card sorting machine. This is from the 1890s, so way before electronic computers. So Hollerith was the founder of a company called the Tabulating Machine Company, which later merged with others and became IBM. So you can view this as the beginning of IBM. And the issue here is with the US Census. So you've all heard about this census in the news, whether we should approximate. But you know, every 10 years in the Constitution it says the U.S. has to count up everyone in the country, okay, and it has to record statistics about them. Okay? The problem is there are a lot of people in the U.S., and even in 1880 there were a lot of people in the U.S., and you had to count them all. And that took a long time. So to do the 1880 census took almost 10 years. So they were a little worried that for the 1890 census it would take more than 10 years because, you know, there were more people then. And, well, the census is supposed to be complete before the next one begins. Otherwise, all hell breaks loose. So for the 1890s, Hollerith and a bunch of people competed for a good machine to automate this process and make it go faster. And Hollerith won. So he was a lecturer at MIT when he did this, when he prototyped these machines. Then he worked for the US Census. I keep putting my pages all over the place. And to count how many people there were, to get the total tabulation took 6 weeks for the 1890 census, which is a lot faster than 7 years or whatever it was. So this was a big improvement. This is sort of the beginning of card machines and card-based computing. And Charles brought some cards just to give you an idea of what they look like. You know, cards are not totally obsolete. Believe it, I've never used a card machine. Don't worry. And I doubt that most of you have. But cards are still in active use.
So this is an IBM card, which many of you may have seen. Who here has never seen an IBM card? Good, good. Yeah, you haven't missed anything, let me tell you. This is what I originally started programming on. So let me pass that around. And then the cards were chosen because they were the same size as cache of the day, so they could use cache boxes to store them. And as a consequence, since there were many people who had them, they started making voting ballots out of, and if you actually tear off this part, which is what they do, you end up with something that's exactly the same size as that data processing card. Okay, and these two are Florida ballots. Pass around as well. Okay, and these are some more there are demonstrator ballots. They're the same. I mean, they weren't Florida ballots, but they're the same kind. If you folks want, you can punch some hanging chads in the cards as I pass them around. If you want to play with them.
So that's your history lesson. So I'm sure Charles would like me to say a little bit about IBM cards. So whoever has the IBM card, can you hold it up? Yeah. So you notice it's longer in one dimension, right? And it's a grid of places where you can punch holes. Okay. And the height is 12. So there are 12 places for each column. There are 12 spots you can punch. For each row, how many positions do you think there are across? Any guesses? 100, 10. It's longer than 12. 144, close. It's 80. Yeah, you're on the right track. So if you ever wonder why terminals have 80 columns, blame it on that card. That's the reason. Okay, so each of those cards encodes one line of text. Okay, it looks two-dimensional, but in fact, these are the characters and this is the data. So you punch certain holes in combinations to get letters and numbers and things like that. Okay, so that's your history lesson. And you can read, and I think linked from the lecture notes in the PowerPoint file, is Hollerith's original patent about this stuff. And Hollerith wrote in his patent how to use these machines. Okay, I should say how these cards are used. So there's this cool contraption. You can see pictures of it on the web, where you have this big stamping machine. You put your card here. You pull it down. It looks at the card. Certain holes go through and connect to mercury, right? And that makes the circuit. And so, and then it reads the data. Okay, in this operation. there are a bunch of counters for counting how many people there are, how many males, how many females, these sorts of things. They automatically increment by this operation. And furthermore, to your side, there's a bin of buckets, like 12 buckets, I think. And you pull this down, and the machine automatically opens up the right bucket. So you say, I'm interested in this column. It'll open the right bucket. You put the card into the bucket. You close the bucket. You take the next card. So this is in the good old days when an algorithm actually involved a human to execute, which is kind of a fun notion. And that was a lot faster than sorting by hand. The tricky part is you could only sort one digit at a time. So now the question is, how do you sort your whole number? If you have, I don't know, a 4-digit number, how should you sort it? And the natural thing to do, and this was what Hollerith wrote in his patent, is you sort by the most important number first. That gives you a bunch of piles. Then you take each pile and you sort by the second number, second digit. And then that gives you more piles, and then you sort each of those piles by the third digit. And you get lots of piles, and this is sort of annoying. So if you sort by the most significant digit first, that's a pain. And the really cool idea in radix sort is to sort by the least significant digit first. Okay, you all know that the problem set 3 is on the web page. So this I think is a really cool algorithm. So the idea with radix sort, when I saw this, I mean, I was just so amazed that it worked. You sort by the least significant digit first. And you do that with a stable sort. So let's call this, you have to use another sorting algorithm to get this to work. So I'll call it the auxiliary sorting algorithm. And so a typical choice for that is counting sort. Okay, so we're going to use counting sort. We'll sort by the least significant digit. Then we'll sort by the next least significant digit. And we keep going. And we only have one pile at a time. Very cool. And this presumably was discovered by the people who used this machine. Hollerith said to do this, but I'm sure eventually people thought, well, if we go backwards, it just seems to work. It sorts perfectly. I mean, I don't know about you, but at this point, I have no intuition why this works. It's actually very simple, but we have a fair amount to do, so that I need to speed up a little. Good. So this is the right idea. And let's do a quick example. So suppose I have these numbers. So each of these is a 3-digit number. Okay, I want to sort them. And this is the most significant digit, so I will sort by the least significant digit. So I'm looking at this column. I say, OK, let's sort that. Sort by this one, stably. So they're repeats, right? There's 2 9s. I'm going to keep this one above this one. Okay, it won't matter much in this step, but it will matter in the future. So smallest is 0, then 5, then 6, then 7, and then 9. Did I get them all? I missed one. Which one did I miss? Here? 839. Ah, thank you. Here. Whew. I was lucky. I missed a good one to miss. Okay, so now we've sorted by this column, right? This is sorted. Now we look at the next least significant digit and sort by that. So the smallest now is 2, and there are a couple of 2s. And we'll keep them in order, like they were before. Now there's 3s, 2 3s. Keep them stably ordered. Next, 5. There's a bunch of 5s. Okay, the key thing is now if you look at these last 2 digits, they're actually sorted by those 2 digits. Cool. And lastly, we do this column. And smallest is 3s. Then the 4s. Then 6. 7, and 8. I think I've got them all. And look, they're sorted. So now, hopefully you believe it. Let's prove that it works. Anyone have an idea how to prove that this works? Whenever I ask that question, pretty much it's always the same answer.
Loop invariant like n digits or so, and will be sorted after.
Right. Yeah, that's good. We'll use a loop invariant by which digit we're at. So I would just say induction, but it's a loop invariant. I didn't write this as a loop, but it is. So for correctness, we'll induct on which digit we're sorting in. Let's call that digit t that we're currently sorting in. So we'll assume by induction that each number, that this collection of elements is sorted by the last t minus 1 digits. And then we want to sort by the tth digit. And we'll use our stable sorting algorithm. And so now we want to look at, suppose we have 2 elements that differ on the tth digit. Well, how do you write teeth? It's TTH. So I use 2 different T's. T-E-T-H. I don't know. T-E-E. Oh, teeth. Of course. Yeah. Okay. Good. So if we have, let's say we're sorting here. We know that we're already sorted by this element. Now if we have 2 numbers that differ, 3 and 5, well, we're sorting by that digit. So this one will go above this one, which is what we want, because this is more significant than this. Okay. That was an example where they matched, but here they're in the opposite order, right? They happen to be sorted by 5 is less than 6, but I want them in the other order because this is more significant. Good. So these guys are put in the right order by this iteration. And the other kind of pairs of elements are elements that are the same on the tth digit. And those, the algorithm doesn't play around with, right? As far as this sorting iteration is considered, they're equal, and so we'll keep them stable, keep them in the same order as they were before. So they're left in their original order, which is correct. That's what you want to do. So if you have two values that have the same middle digit, well, then you want to sort less significantly by the last digit, which is what we've already sorted by in this iteration. So these two will be left in the same order over here. So in all cases, we're doing the right thing. Good. That's the correctness. I'm afraid I have to do a little bit more, which is how fast does this algorithm take? Sorry. How long does this algorithm take? How fast does it run? So let's suppose that we're using counting sort as our auxiliary sort. Okay, how long does this algorithm take? Well, it depends on how you treat your numbers as split into digits. Okay, we're not necessarily given numbers laid out for us like this into separate digits. With cards, you were, but in binary computers, it's a bunch of bits. We could cluster bits into digits if we wanted. And that would affect how many passes of counting sort we use, and that'll affect how long the algorithm takes. Right, so let's suppose we want to sort n words of b bits each. So we have a word that looks like this. Well, we can carve that word into however many pieces we like and treat each of these as a digit. So let's say that the length of one of these subwords is r. So each of these is r. And so there are b over r chunks that we've divided our number into. So split each b-bit word into r bits. And so there are b over r passes through the algorithm. B over r times we call counting sort, one for each digit. So the running time let me give the arguments here. This is depending both on n and b, and in fact on r. But we can choose r however we like, so we'll choose it to minimize the running time. So what's the running time here? Okay, so remember, we're doing b over r passes of counting sort. And what is the value of k in counting sort? K was the largest possible number, which here is... So how big can these digits get? 2 to the r. It's actually 2 to the r minus 1, but let's say 2 to the r. Good. Yeah, it's actually exactly 2 to the r. So how long? Now counting sort took order n plus k times. So what's the total running time? Do some computation. Sorry? Right. B over r, that's the number of iterations we have, times the quantity n plus k, and k is this. So n plus 2 to the r. Now, we want to minimize that function. So the easy way is you differentiate it and you set it to 0. And that'll tell you really where the minimum is. But that's cheating. So, that's just using computation. Let's use our intuition. See, what is this function doing? I'm allowed to change r. If I make r bigger, this gets smaller, which is good. I use fewer iterations. But if I make r too big, this term gets really big really fast. So I better not make this much bigger than that. Okay, I better not make 2 to the r much bigger than n. This is intuition. This is the right intuition. Because this r term is not too significant. We'd like to make r big so long as this is not much bigger than that. So r better not be much bigger than n. Okay, so I won't write down that intuition because we're out of time. But let's just choose r to be log n. And then the time t of n comma b for radix sort is theta b over r. Oops, sorry. That's the original recurrence. It's now b n over log n. If you compute it out, which is pretty good. So, for example, if the numbers that you're dealing with are in the range, let's say 0 up to n to the d minus 1. So you have n numbers. Let's suppose all the numbers are bounded polynomially. So d is some constant. So if they're all at most n to the 100th power, which is pretty big, then the running time is theta d times n. You have d iterations. You split each number into log n bits, which has a value from 0 to n, roughly. And you need d of these words. So the total number of bits here is d log n to represent a number of that size. You carve it into pieces, each of which is log n bits. So there's d of them. So that's the running time. And that's linear time if d is constant. Now, counting sort, all the numbers had to be at most n for it to be linear. Now, you can get polynomial-sized numbers and still linear time. This is cool. Radix sort is really simple, and it's really fast in practice if you have big collections of numbers. Sadly, it doesn't work so well on modern computers with big caches and things because it doesn't have good data locality. So in fact, a lot of the time, if you tune your quicksort algorithm, quicksort will run faster. But definitely, this is a cool idea. It's great in theory. And for big data sets, it's great in practice. Thanks.